So guys, I want to talk a little bit about differential equations just as an end to this course. This is something that you're going to be doing in more detail and in a different way actually in EM 202. Whoever takes that, I'm not sure who's giving that. And you're going to be using what are called Laplace transforms to solve the equations that we're going to look at today. And it's a different way, different approach, but this way that we're going to do is perfectly fine, and it's perfectly valid. But but the Laplace transforms are typically the way that engineers solve these equations. But to me, they're unnecessary. You don't need to do that. You don't need to use Laplace transforms. But it's a choice. You can either do it this way, I'm going to teach you now, or you're going to use the differential or the Laplace transforms way. It's fine. But the first question is, you might ask yourselves, like, what are differential equations and where do they come from and what do they want? Okay, so an analog system, guys, is anything that takes an analog signal and transforms it into another analog signal. And an analog signal is a signal with continuous input. It's got a value, we say, at every moment in time. So that's what an analog signal is. And those of you who are in electronics, you've probably done analog systems as a course even. Okay, so an analog system takes an analog input and it converts it into an output, an analog output. And as I say, and that's what, this is kind of a very kind of meta and very just kind of a general kind of discussion as to where the differential equations come from. But the important thing though is that you've got a system, you've got an input, which I'm calling f of t. T usually stands for time. And I've got an output, y, brackets t, which signifies that y also depends on time. All right? And the game here, guys, is to make a prediction for y if you know what f is. And so you're putting something into the system, and as an engineer, before you put the input in, you want to be able to predict what the output is going to be, to make sure that the system, for instance, doesn't fail, for instance, because all systems have ranges at which beyond which they'll fail. So you want to make sure perhaps that the system won't fail when you put in a particular input. Now, it's not an obvious thing and it depends on the different application, but you can have every analog, what's called a first order system, is described by a differential equation of this form. And if you look at the differential equation, it's kind of a very neat formulation as to what's going on. Now, on the right-hand side there, you've got the output. And on the left-hand side, you've got some combination of y. And y is your output. And a first-order system is called a first-order system is because you have a first derivative of y. And your game, or your goal, or your mission is to find out what y is in terms of t. Because the letters A and B, they're constants, they're physical constants, which you will know from the system. And f brackets t is your input, which you also know. So in this equation, you know A, you know B, you know f, but you don't know what w is. You want to find out, not w, y, and you want to find out what y is. And as I say, I'm not going to go into the nitty-gritty as to how the differential equation describes the particular first-order analog system, because it depends on the system itself. Okay, so I'm not going to go. This could be something, for instance, a simple circuit. For instance, very simple circuit. So you have a dy dt plus by is equal to f brackets t, where f is the output, f is the input, y is the output, a and b are known. Now, attached to a first-order system, you could have what's called an initial condition, which tells you what the output is at t equal to 0. And I'm saying that that value is capital A. It can be anything you like, any letter you like. So this is usually, not always, you have what's called an initial condition as well. So you have a differential equation and you have an initial condition, which tells you what the system is like initially at t equal to 0, and then the differential equation above there predicts what how the system is going to behave for all times t greater than 0, for all other times. So you know what the system is like at the beginning, how does it evolve over time, and how a first order system devolves over time is by means of the differential equation. And you have to find y in terms of t, or you have to what's called solve the differential equation. So your goal is to find y in terms of t, and if you can do that, you've solved the differential equation, and you can make a prediction, because remember what y is your output, so you're making a prediction of what the y or the output is at any given moment in time. All right, so that's the first order system, and you probably will hear that terminology in some other courses. Those of you who the mechanical side of things will be doing things called control, and first order systems are very important in control, and maybe electronics guys, you do control as well, maybe, I'm not sure, but you should do, no judgment here, if you're not doing it, that's fine. Yeah, so you will come across this terminology, and a first order analog system is a system whose differential equation is given by the differential equation there on the slide. Now, first order systems are relatively straightforward and very simple systems, and so you can actually have more complex systems. And one of the more complex systems we're going to be talking about, the more complex system we're going to talk about is a second order system. And a second order system is described with the differential equation there on the slide. And it's called a second order because the output y is differentiated twice with respect to t. Now, if a in that differential equation was 0, you're back to a first order system. So therefore, in a second order system, a is not 0. All right, b and c could be 0, but a can't be 0 in a second order system. Now, again, guys, f is your input. A, b, and c are constants of the system. They describe how the system behaves. And y is your output, which you need to find. Now, because this is a second order system and you've got a second derivative, you've got d squared y dt squared, in order to determine how the system behaves, you need two conditions here. Now, you can either specify the two conditions at a single point, and then you have what's called an initial value problem. And with initial conditions, for instance, y at 0 is equal to a, and y prime of 0 is equal to b. Now, hopefully that notation, you're familiar with that notation. Y prime or y dot denotes the first derivative. So y prime at 0 means dy dt evaluated at t equal to 0. So you can either have that system, which is called an initial value problem with two initial conditions, or you can have what are called boundary conditions, and then you have what's called a boundary value problem. And in the boundary conditions, you have the output y specified at 2 points in time, usually. So you have y at a, say, is equal to b, and you have y at c equal to d. Now, don't worry about this. And I don't even want you to worry about the terminology, but you might hear the terminology. And when I was your age, I wasn't sure what the difference between an initial value problem and a boundary value problem is. And there isn't that much of a difference. It just depends, it's just a way of classifying the conditions associated with the differential equation. Okay. But the important thing here, guys, is your mission, your goal is to find y in terms of t. So you want y equal to something involving t. That is the goal. Okay. Now, if there's no input into the system, the corresponding differential equations are said to be homogeneous. And these are very, very important. And this distinction is very, very important. So you have what's called a first order homogeneous equation there, because if you look back on the previous slide, we had equals to f of t, but f of t is equal to 0, then you have that differential equation. And a second order homogeneous differential equation there is given by that equation. A d squared y dt squared plus b dy t plus cy is equal to 0, where a, b, and c are constants. Now, if there's no input into the system, well, you might wonder what is driving the change in the system. And what's driving the change in the system are the initial conditions or the boundary conditions. That's what's driving the system in that particular state. Physically, that's what's going on here. So you can imagine, I suppose, my example, and I'm sure if it's not a great example, but if you have a piece of string or a piece of elastic, and you stretch it, and then you take the elastic and you raise it a little bit and you let it go, then the elastic band will vibrate up and down. There's no input into the system there, but what's giving the equation the energy to move is your initial condition. So, but again, though, guys, from you don't really, I don't care in this particular course. We don't care what is going on in any particular system. All you care about is solving differential equations. And you need to, and this little movie is talking about solving first order and second order homogeneous equations. All right? And how you do it actually, well, the way we're going to do it is very simple. It's actually pretty much the same method for both cases, which is nice. So we're going to look at first order homogeneous equations first. And the way you do it, guys, is you essentially guess the solution. All right, and the reason why you can guess the solution is because people have been studying these things for hundreds of years. And after hundreds of years, they know that if you have a first order system, then the solution is an exponential. All right, and that's why the exponential function is so important in engineering, because it describes the response of first order analog systems. All right, so but essentially what we're doing here, guys, and if you had a differential equation, it would probably never occur to you to do this. Why would it? But as I say, we are the beneficiaries of people studying these things for hundreds of years, and so we know now what the solution is, and we don't have to worry about any other solution, essentially. So what you do is you guess a solution of the form y is equal to alpha exponential mt. And you substitute that into the differential equation, and you solve for m, the exponent. Okay? And you get alpha then from the initial condition or the boundary condition. We'll do an example in a minute, don't worry. Okay? So we'll do it now, actually. So let's solve 3 dy dt plus 5y equal to 0. Now, guys, remember what the goal here is. We want y in terms of t. That's the goal. So what do? Well, you substitute y equal to alpha exponential mt into that differential equation. So you let y is equal to alpha exponential mt. We need dy dt in order to substitute into the differential equation. And when you differentiate alpha exponential mt, you get alpha m exponential mt. Because when you differentiate the exponential, you must differentiate inside the exponential with respect to t, and you get m. So if y is equal to alpha exponential mt, dy dt is alpha m exponential mt. And now we can substitute in. And when you substitute in here, guys, you can bring the alpha exponential mt term outside the brackets because they're common. And what you're left with inside the brackets then is 3m plus 5. Now, alpha can't be 0 because that would be the 0 solution. Exponential is never 0 because it's the exponential function. It's never 0. So the only way that equation there can be true is if 3m plus 5 is equal to 0. Or m is equal to minus 5 over 3. And so therefore now you've found out what m is, and therefore your solution is alpha exponential minus 5 over 3t. And that is it. Okay, it's that simple. Okay, so you're guessing a solution essentially, but you're guessing, it's an informed guess, and it's informed by people, the smartest people in the world studying this for a very long time. You substitute in that guess, you find the solution for m, you get your value for m, and then you just write down the solution, essentially. So there's no actual mathematics going on here. Excuse me, guys, I just sneezed there. So there's very little mathematics here. You just solve for m there, it's 3m plus 5, that's it. Okay. So now let's look at an equation with a condition associated with it. Woo. So forget about the condition initially, guys. The condition, the y at 0 equals 2 thing, forget about it initially. So let's look at the differential equation. Again, you let y is equal to a, or alpha exponential mt, so therefore dy dt is alpha m exponential mt. You substitute in there, you bring the alpha exponential mt outside, and you get m plus 4 is equal to 0, so therefore m is equal to minus 4. So your solution to the differential equation is alpha exponential minus 4t. Now, we can determine alpha here because we're given a condition. We're told that y bracket 0 is equal to 2. So that's telling you that at t equal to 0, y is equal to 2. Okay, so then you go to your solution. You replace y by 2 and t by 0. And because the exponential of 0 is 1, you're going to get 2 is equal to alpha here. And so then your solution then is 2 exponential minus 4t. And it's that simple. Okay, so there is no excuse for not being able to solve first order equations like this. Now, these are very simple first order equations, and I'm not sure, I think you did last year. If you can remember last year, I can't remember last year. I think we've always been doing this nonsense. We've been cowering away from COVID for the last 20 years. But I think last year you might have done more sophisticated equations, much more difficult equations with Connor Brennan, maybe? I'm not sure. These differential equations that we're looking at are very simple because if you look at the differential equation, you've got dy dt plus 4y is equal to 0. The terms multiplying the derivative, the dy dt, is a constant, it's 1, and the term multiplying the y, 4, is a constant. So these are very, very simple equations. They're called first order equations with constant coefficients. But nonetheless, these are very, very important and describe very many engineering systems. And you should know how to solve it. Now you can, right? Look at this. It's that easy. It really is. All right. So they're first order equations. How you solve second order equations, homogeneous equations, is pretty much the same. You let y is equal to alpha exponential mt and off you go. All right. So let's look at a homogeneous second order equation. And remember what a homogeneous equation is. It's a second order equation equal to 0. So again, guys, you let y is equal to alpha exponential mt. You need the first derivative, which is there. But in this case now, because you have a second derivative, you need a second derivative. You've got a second derivative in your differential equation. So you need to find out what d squared y dt squared is when y is equal to alpha exponential mt. And there it is there. It's alpha m squared exponential mt. You substitute each of those three terms into your differential equation. And you get that. There's an alpha exponential mt term common to each of those three terms. You bring it outside. And what you're left with inside then is am squared plus bm plus c is equal to 0. And alpha can't be 0 because otherwise nothing happens. Exponential is never 0. So the only way that this is equal to 0 is if am squared plus bm plus c is equal to 0. And that equation is a quadratic equation for m. And because it's so important and it occurs so frequently, it has its own special name, and its special name is auxiliary equation. Okay, so it's am squared plus bm plus c is equal to 0. Now, a, b, and c, as we will see, will be given to you. You know what they are, and so you can solve for m. Now, this is a quadratic equation, guys, and again, the famous quadratic formula is what you use, and this is what you get. So you get m is equal to minus b plus or minus the square root of b squared minus 4ac over 2a. Now, guys, the problem with homogeneous second order equations is that there are three possibilities for m, actually. And it's not obvious. Well, maybe it is obvious. No, it's not obvious. But there are three possibilities. Because you've got the square root of b squared minus 4ac. Now, if b squared minus 4ac is positive, you have two real roots, which is fine, which is great. If b squared minus 4ac is equal to 0, then you have one solution for m, and only one solution for m. And if b squared minus 4ac is negative, you have complex roots for m. And so depending on what the sign of b squared minus 4ac is, you'll have different forms of solution for second order homogeneous second order equations. So this is where it gets a little bit tricky. But the thing that to remember when you're solving homogeneous second order equations, guys, is that there is no mathematics, essentially. There's none. You just remember what the solution is. And the only mathematics you have to perform is solving a quadratic equation. And that's it. So that's pretty nice, actually. But you do have to remember, for each of those three cases, you have to remember, keep in your brains what the solution is. So let's have a look. Suppose b squared minus 4ac is positive. And so you get two real roots. Let me call them m1 and m2. In that nice situation where you've got two real roots, m1 and m2, the solution to your differential equation is of that form. You have to remember this. There's no mathematics, it's just write it down. And how can I write it down? How do I know that's true? Because people smarter than you and I have done this and said this is the solution. So you just accept this, all right? So it depends on what the values for b and a and c are, the size, the relative size of them. But if b squared minus 4ac is positive, you have two real roots and call them m1 and m2, and you get this solution here. All right, we'll do an example in a minute and kind of bring out how easy this is. All right, suppose b squared minus 4ac is equal to 0. Then you have only one real root. There's only one solution to your quadratic equation. And you have to remember what the form of the solution to the differential equation is, right? It's c1 exponential mt plus c2 t exponential mt. All right, so there's an extra t term there cropping in, popping up, popping in, whatever the expression is, when you have only got one real root, right? So it's not obvious that that's the case. And why is it t and not t squared? It's because it's the way God made homogeneous second order equations. All right, this is just the way the universe works. I did not make up the rules, folks. These are just the rules. Okay, so you get two. You get y is equal to c1 exponential mt plus c2 t exponential mt, and the last case you have to worry about is when b squared minus 4ac is negative. And when b squared minus 4c is negative, you get what are called, you get complex roots. You get two complex roots. Okay, so this case is the more complicated, the most complicated case, and you have to do a bit of arsing around. It's actually easier when you actually start looking at problems, but in general, you have to do a little bit of messing about. So here's the messing about. We know that b squared minus 4ac is negative, so therefore 4ac minus b squared is positive. All right, so you can rewrite what's inside the square root sign as I did there, minus 4ac minus b squared. 4ac minus b squared is positive, and you're multiplying that by minus 1. So you can bring the square root into each of those individual terms. So it's the square root of minus 1 times the square root of 4ac minus b squared. We call the square root of minus 1 I. That's by definition. And so therefore what you end up with then is minus b plus or minus I, the square root of 4ac minus b squared over 2a. And let's call the real part alpha and the imaginary part beta. Okay, so alpha in this case is minus b over 2a, and beta is the square root of 4ac minus b squared over 2a. It will be easier when you start doing problems, guys, as you will see in a minute. So alpha is the real part of your complex root, and beta is your imaginary part of your complex roots. So your solution is exponential alpha t times c1 cos beta t plus c2 sine beta t. And why is it of this form? It's the way the universe works. That's it. Just the way it is. This is the way the universe works. When you've got complex roots, you'll have a cos and sine term multiplying an exponential. And again, guys, when you look at this here, you have to remember for each of these three cases, you have to remember what the form of the solution is, unfortunately. But there is no mathematics. The only mathematics you have to perform here is solving a quadratic equation. All right. So let me do a few examples quickly. Right, this is example 1. Suppose I wanted to solve d squared y dx squared plus 5dy dx minus 3y is equal to 0. Now you have to be careful now, guys, with the notation here. We've got d squared y dx squared, so we want y in terms of x. It's what's above the line in terms of what's below the line. That's our goal, y in terms of x. Now, you can do the usual. Oh, that's not right then. This is not correct. I just copied it from the previous slides, but it's incorrect. I should be substituting y is equal to alpha exponential mx there, and then I have dy dx equal to that, and d squared y dx squared is equal to that. Now you can do that, and that's fine, but here's a much quicker way, guys. You can short circuit all the substitution and write down the auxiliary equation straight away from the differential equation. It makes it much more efficient, right? So the auxiliary equation corresponding to that differential equation there is 2m squared plus 5m minus 3, and that's it. So for the second derivative, you'll have m squared. The first derivative, you will have m. And for the y term, you just have 1. And that's actually the basis of what is called the Laplace transforms. That simple idea. So you can substitute in y is equal to alpha exponential mx and do the messing about, but you always end up with the same auxiliary equation, the same quadratic equation. And my advice to you guys is when you're solving a second order homogeneous equation, is just to write down the auxiliary equation straight away. And in this case, it's 2m squared, because m for each different derivative you have an m, 2m squared plus 5m minus 3. Okay, be very careful with the last term. It's not minus 3y or minus 3m, it's just minus 3. You only have an m when you have a derivative. Okay? Now you need to solve that. I can factor that, I think, like this. Now you can use the quadratic form if you want to, but I think if you factor, you get this. So then you get m is equal to 1/2 and m is equal to minus 3. These are two real roots. So your solution is that. And you walk away into the second half of second year. This is just a joke. All right? And in the end here, on the last line here, I did correct myself, guys. I've written y in terms of x. Just be careful with that. Be careful with that, because you want y in terms of x, not y in terms of t, or t in terms of x, or whatever it is. Just write down the variables that you're given. All right? So in terms of solving second order homogeneous equations is equivalent to solving a quadratic equation. I mean, come on. And remembering then what the form is for each particular form of the differential equation, or for each of the forms of the quadratic equation. So this is the simplest case, I think. When you've got two real roots, then it's just c1 exponential the first root times x plus c2 exponential the second root times x. And it doesn't matter what the order. You could have c1 exponential minus 3x plus c2 exponential 1/2x if you wanted to. That's fine. It doesn't matter what the order. Okay? And c1 and c2 are constants. They're arbitrary constants. Now, let's look at this differential equation. Now, this is what's called an initial value problem, because you have a differential equation given here, and you've got two conditions associated with that differential equation. And you have two conditions here because you have a second order derivative in your equation. You've got d squared x dt squared. So you need two conditions, right? And your conditions are given here at 0. You've got x at 0 is equal to 0 and x dot at 0 is equal to 1. Now x dot means dx dt. So that's a usual notation. Prime and dot are notations that people use sometimes to denote derivatives. Okay, dot notation is usually reserved for differentiation with respect to t, but it doesn't have to be, all right? So what you do here, guys, what you do here is, you can forget about the substitution, just write down the auxiliary equation straight away. You'll have m squared minus 4m plus 4 is equal to 0. You can factor that, that's m minus 2 to be squared, so you just get m is equal to 2. There's only one solution for m here. So then your solution then must be x is equal to c1 exponential 2t plus c2t exponential 2t. By definition, essentially, when you have one root to your auxiliary equation, your solution must be an exponential of the root plus t times the exponential of the root. Okay? And that's what you get. Now, we need to apply our two conditions. X brackets 0 is equal to 0. So that's telling you that at t equal to 0, x is equal to 0. So you replace x by naught in this case, and you replace t by naught. And so when you do that, you get 0 is equal to c1 by 1, because exponential of 0 is 1. And c2 by 0 is 0. So you get 0 is equal to c1. Okay, so c1 is equal to 0. So therefore x then is just c2t exponential 2t. Now for the second initial condition, you need to differentiate x. When you differentiate x here, guys, you use the product rule. So x dot is c2 into, you differentiate the t, you get 1 exponential 2t, and then plus 2t exponential 2t, because when you differentiate the exponential, you get the exponential, but you must differentiate inside the exponential as well, you get 2. We're told that at t equal to naught, x dot is 1. So you replace x dot by 1 and t by 0. And again, use the fact that exponent of 0 is 1. So I think in this case, guys, what you get is that 1 is equal to c2. So c2 is equal to 1. And therefore, your solution to the initial value problem here is t exponential 2t. And you walk away into the second part of second year, whistling, full of confidence, full of pride. All right? Okay. Last one, we're going to stop. Let's look at this differential equation. We want y in terms of x here, guys. You write down the auxiliary equation. M squared minus 4m plus 13 is equal to 0. You use the quadratic formula, and you get 4 plus or minus b squared, which is 16, minus 4 by 13, which is 52, all over 2. 16 minus 52 is minus 36. And you can write the square root of minus 36 as 6i. So you get 4 plus or minus 6i over 2, which is 2 plus or minus 3i. And then all you remember then, oh, I've got complex roots. The real part is going to be inside my exponential, and the imaginary part is going to be inside the cosines and sines. And be careful with the imaginary part, folks. The imaginary part is 3. It's not 3i. The imaginary part is the number multiplying the I. So there's your solution, and you walk away. All right, so it's exponential 2x, c1 cos 3x plus c2 sine 3x. And that's it. So all you're doing here is you're solving a quadratic equation and remembering what the form of the solution is if you have complex roots. And that's it. All right. Right, and we're almost there now. I just want to do a little bit more on what happens if you have an input. So what happens if the differential equation is not homogeneous? How do you solve then? And it's a little bit extra. You essentially do exactly the same thing, but there's a little bit extra. There's one more step that you have to do. Okay, guys, I'm going to stop here. And thanks for your attention. And I will see you later.